Hello everyone, my name is Pranal Gupta. I'm a master's student at the University of Waterloo. Today, I'll be presenting our work on columnar storage and list-based processing for graph database management systems. In this work, we explore the applicability of existing techniques from columnar relational database systems and also propose new solutions to adopt them in context of a native graph database systems. We base our work on GraphLoDB, an in-memory graph database system optimized for performance and scalability that we are developing at the University of Waterloo. Graph database management systems are read-optimized systems that are known to support read-heavy workloads containing large number of many-to-many joins. These systems are tuned to perform fast joins on many-to-many relationships that is a unique characteristics of the graph data. They are able to do so by making use of adjacency lists that maps a vertex to its set of neighbor vertices and corresponding edges. Typical applications of GTVMS include fraud detection, recommendation systems, and social network analysis. To establish the relevance of columnar techniques for GTVMS, note that columnar stores too are optimized for read-heavy workloads that involves reading and processing large amounts of data sequentially. For this, they employ a number of techniques. Firstly, tables are stored column by column and not row by row, which allows sequential read of values of an attribute from all rows with good cache locality and reduced number of IOs. They employ specialized compression schemes for each column based on the type and distribution of data in that column. They process data in blocks as opposed to one tuple at a time. Consider a query to count number of persons in a city and a simple plan that scans the city of the person, filters, and finally aggregates. In traditional volcano style processing, this happens tuple at a time, starting from P1, P2, then P3, and finally P4. This does not exhibit good cache locality as the reads are random. In comparison, block-based processor reads all of person city column together. Then it filters and finally aggregates in a tight loop. Here, sequential read on chunk of data leads to better CPU utilization. These techniques are highly relevant in context of GDBMS and hence can make them more competent. However, as I demonstrate next, these techniques cannot be directly applied as the two systems differ in their data access patterns and workloads. In this talk, I'll demonstrate only two differences, while the others can be found in a paper. The first difference is that the two systems differ in data access. Columnar systems are optimized for queries performing sequential access on large chunks of data. A textbook query for this can be one heavy on filters, group bys, and aggregates, like the one shown here, which count number of persons in each cities. For this, the system simply reads the city column sequentially and counts two group of values in it. In contrast, a typical query in GTVMS is like finding friends of a person and operating over their properties. Such queries too access large amount of data, however, they now do so randomly. Consider a one-hop query which reads the age of Alice's friend. Our plan scan all persons and filters Alice, which is node P3 in our representation, then joins it to neighbor node and finally reads age property of that neighbor node. Suppose we have filtered Alice, then the join operator reads the first element from the Alice forward adjacency list, then read the age property. This happens for other values too in the adjacency list. Hence, as we can see here, reading properties are random. One implication of this difference is that the compression in columnar stores need not support decompressing random elements from a compressed block, since the reading is always sequential, whereas graph systems need random access, for which they should be able to do random reads in compressed block without having to decompress the block. Hence, the columnar compression techniques cannot be directly adopted. The two systems also differ in the nature of joins they perform. The joins in columnar RDBMS are predominantly primary key foreign key joins which do not grow. That is, there is no explosion in the number of intermediate tuples produced, and hence nearly no data replication. However, in graph systems, joins are typically many to many. As a result, joins grow rapidly, that is, the number of intermediate tuples explode with lots of replication. that is, increases with the number of joins in each query. Same is shown in the illustration here, where we find Alice friend of friend. The intermediate tuple grows from one tuple to 3 and then to 9, with Alice repeated in each tuple. As we demonstrate later in the talk, block-based processing employed by columnar stores are not optimized for performing joins because of this data replication. So, direct application of block-based processing can give suboptimal results. I'll limit the number of differences here and hence next move to the contributions of a paper. Columnar techniques cannot be directly adapted and hence require redesigning to suit our requirements. Our work study these requirements and proposes new design across storage, compression, and query processing. We identify techniques that are directly applicable, for example, vanilla columns for vertex properties and dictionary encoding compression. Where direct application is not feasible, we design new techniques like the single indexed edge property pages, a new edge ID scheme that can be highly compressed in adjacency list, a null compression scheme that allows random reads from compressed data, and finally, a list-based processor. For the scope of this talk, I would only discuss list-based processor. Other techniques can be found in a paper. To motivate our case for a new query processor, we first revisit the design of the block-based processor. Traditional block-based processor falls short of being performant on many-to-many joins. That is the USP of the graph data. Consider a two-hop query on person nodes with a filter on age property of start node. I use a simple left deep join plan that scans a person, filters by age, and then joins from A to B and B to C. The block-based processors start with a single vector with all person node IDs. It then reads the age column and performs filter sequentially. The result of filter is stored in a bit mask vector. It will then join all nodes in vector A to the elements of their forward adjacency list by copying them in vectors R1 and B. Here, only part of the intermediate chunk is shown, but as you can see, P2 is replicated twice and P3 thrice. That is the number of elements in their forward adjacency list respectively. Similar replications happen on the next join too, as can be seen in vectors A, R1, and B. Hence, as a shortcoming, there is a high replication of data in intermediate data chunks. Reason being that the intermediate data chunk represents the set of flat tuples in a single group of vectors. Each row in the data chunk is a resultant tuple. Also, if we go back a bit, notice that the contents of R1 and B are exact replicas of the adjacency list P2 and P3. That is kept in the memory for an in-memory GDBMS. Hence, we can prevent this materialization of adjacency list in our intermediate data chunks. The second shortcoming here is that the block-based processor copies exact replicas of adjacency list in intermediate data chunks. We address the shortcomings of block-based processor with a list-based processor that is based on two key concepts. First, we use factorized representation that was given by Altenew in 2016 to succinctly represent joins as a union of product of independent components. Using this representation, the intermediate data chunk after one join of query on last slide can be given as the union of product of two components, the singleton lists P2 and P3 and forward adjacency list of P2 and P3 respectively. Second, our implementation uses list groups. In our implementation, a single intermediate data chunk is made up of a number of list groups, which has these three properties. First, a list group can be either a single tuple or a list of tuples. Second, the size of the list group is not fixed and takes the size of the adjacency list that it holds. And finally, the list group do not materialize these adjacency lists and just hold the pointer to the relevant adjacency list in the memory. I now run a simulation demonstrating a list-based processing. Consider the same two-hop query and the query plan as before. The scan operator now creates a new list group called LG1 with a vector A containing person nodes. Each list group has a current index field that is either -1, which means all tuples in the list group are part of the intermediate data chunk, or it can take a positive value, meaning the list group is flattened and represents just a single tuple. Here, currently LG1 is unflattened. Next, the filter operator operates on the unflattened LG1 and reads the age property for nodes in A and evaluates the age in mask vector. We then move to join, which in list-based processor does two things. One, it flattens LG1 by setting the current index to 1, since the 0th location is already filtered out. Now, LG1 is interpreted as a single tuple. And second, join creates a new list group called LG2 and reads the adjacency list of P2 into R1 and B. Overall, flattening of LG1 prevents the need to copy a tuple in LG1 with each tuple in LG2. Also, we avoid materialization in R1 and B by instead having pointers to forward adjacency list of P2. The second join follows the same operations, that is, it flattens LG2 by setting current index to 0 and creates LG3 that points to the adjacency list of P3 in memory. The factorized representation at this point of time is a product of P2, P3, and forward adjacency list of P3. Going forward, the second join then increments the current index of LG2 to 1 and reads the adjacency list of P4 to LG3. We experiment list-based processing on LDBC, which is a popular benchmark for evaluating graph systems, along with datasets from other domains as well. To sum up, we get a speed up of minimum 3x and up to 19x on our queries consisting of aggregates and filters. The complete evaluation can be found in our paper. So, to end the talk, I would like to point all towards our project page, graphflow.io, which contains our past research and talks. Also, we have the references here on which we base our work on. Thank you.